well, there's only 5 points. Or if you make it 93, it's 7 points. So it's not as many points that you're gapped out. So
and then you make up a perfect score.
that's crazy. Yeah. Okay, y'all. Let's see. Let's see if we can hear me. Okay, we can. I'm gonna share screen. Y'all excited about homecoming? I know it stinks that there's not a homecoming dance, but you know, at least you get to have football. There for a while, I didn't think we were even gonna get to play football. So, all right, y'all had enough time to do that. Let me answer one more email. That little ding, that's the response to me. Okay, got it. I think I got it. All right, okay, so we are using the midpoint formula. What is the midpoint formula? Anybody? 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 Add the x's. Divide by 2. Add the y's. Divide by 2. Okay, that's too chunky. That's making too much noise. All right, and so then all we have to do on number 1 is add up our x's and add our y's. Now, unlike the distance formula, it doesn't really matter who you start with because the addition is commutative, so it can go either way. So we just have to add the x's together. Divide by 2, add the y's together, divide by 2. So what is -2 plus -12? What's -14 divided by 2? Okay, so our x value is -7. Then what's -8 divided by 6? Not divided by. What's negative 8 plus 6? Negative 2. What's negative 2 divided by 2? Everybody good with this? Easy? Thank you. All right, on the next one, you're doing the same thing, just with the coordinates of the point. So you've got 4 plus 0 divided by 2, and 4 plus negative 4 divided by 2. So that's going to be 4 divided by 2, which is 2, and 4 plus negative 4 is 4 minus 4, so 0 divided by 2 is 0. Find the coordinates of J if K is this, is the midpoint of JL, and find L's coordinates. Okay, so this is one you have to work backwards on, right? Yeah. So we're missing an endpoint, X, plus the other endpoint, which is negative 4, divided by 2, and it's going to equal the X of the midpoint, which is negative 5. Okay, so I just focus on the X's when I'm doing it this way. So I'm multiplying by 2 on both sides. That gives me X minus 4 equals negative 10. Add 4. So X equals negative 6. Yeah? Everybody okay with that? Then to do the Y, I need to do the same thing. I don't know the Y of one of the endpoints, but I know the other one, plus negative 1 divided by 2 equals the Y of the midpoint, which is 8. So I do the same thing, multiply by 2. Y minus 1 equals 16. Add 1. So Y equals 17. Is that what y'all got? So what's the ordered pair for J? Negative 6, 17. Okay. All right. Got it? Good. Cool. All right. Let's look at your homework. I think with this class, we didn't actually finish this lesson. We didn't get to the point about reflectional symmetry and line of symmetry. Did we get that far? We went over in like 2 seconds. Okay. So did we do number 15 yet? Okay, so we did do 15. So just as like a really quick overcat, like go back over it real quick. This has one line of symmetry, not right there. One line of symmetry. Are y'all with me? Y'all with me? Lake, y'all good? Y'all good? Then we've got 2 for that one, and then this one had 6. We connect each of the points, the outer points, and then the creases, the inner creases. So why does this triangle have one line of symmetry and this triangle have 3 lines of symmetry? Did we talk about that? Why are they not the same? Why are all the angles the same? What type of triangle is it? It's an yeah, good. It's an equilateral triangle. So since we have an equilateral triangle, Joseph is right. All the angles are the same and all the sides are the same. All of the sides are going to be exactly the same measurement, so we can have 3 lines of symmetry. Does anybody know the name of this triangle where only 2 sides are the same? Isosceles. Okay, so you have equilateral triangles. All sides are the same, so they're going to have 3 lines of symmetry. Then you have an isosceles triangle where 2 of the sides are going to be the same. You have 1 line of symmetry. And there's one more type of triangle. Do you know what that triangle is? Scalene. Scalene has no sides that are the same, and they have no lines of symmetry. Okay, so it's just a random old triangle. There's no way for you to cut it because there's nothing that is the same. Okay, remember to be reflectional symmetry, and to have a lot of symmetry, you've got to have 2 parts that can be the exact same if it reflects onto itself. Okay, all right, so that kind of just goes over that. This is one I definitely want us to talk about. This, who has infinite lines of symmetry? The circle. Okay, that circle you can cut a million more ways. Okay, so it's just got an infinite way that we could cut it. You could cut it in half here, 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 here. I mean, we could just go all day. Okay, so it just has an infinite lines of symmetry. And then we've talked about this triangle. What about a square? How many does the square have? It has 4, because unlike a rectangle that has 2, it has the same 2 as a rectangle. The difference is the square has all sides that are congruent, so I can cut it on the diagonals and be able to have 4. Okay, so a rectangle only has 2, a square has 4. This rhombus has 2, a isosceles triangle has 1. Okay, so we talked about that super quickly, so I wanted to make sure we went back over that. And like, since I didn't finish with your class, like I didn't post y'all's recording. I went ahead and recorded 4th hour. So if you ever get home and you're like, Miss Cole sucked this morning, like I don't even know what she was talking about, I can't do my homework, you can always go back and look at the video, because if I don't do a good job with this class, I'll record the next class or the next class until I get a good video, and then that's the video I'm going to post. Okay, so just know that that's there for you, and it's on YouTube, so you can just fast forward it to where you need. So if you're like, I didn't really understand the second part of the lesson, get on that YouTube video, go to the second part and rewatch it. And maybe later in the day, I did a better job. Okay. Because what's hard is you guys are my first time to present this. And so a lot of times I'm kind of like working out the kinks with you guys. And then later on the day, I already know exactly what the students are going to ask because you guys ask those questions. So if that does happen, or if you need more help or something, y'all just email me and I will definitely make sure you get what you need. Okay. All right, cool. So the homework was on page 119. And the first thing that we were doing was all those different reflections. Okay, so it wanted you to apply those rules. And really, in order for us to do that, we needed a table with some values of the original arrow. Okay, so if I look at this original arrow, it's got its tip-top point there at 0, 3. Then this is at 2, 2. This is at 2, 4. And we can use the middle again, and that's at 4, 3. So these are my original XY. Okay. Then the next column is going to be the rule that we're going to apply, which is 8 minus X and then Y. So 8 minus X comma Y. So what's 8 minus 0? 8 minus 2. 8 minus 2. 8 minus 2. 8 minus 4. Is this the exact same as the one before in the lesson? No, but it's really similar. Okay, so then we've got 8, 3 as a point. That one was with 0, 3. So that actually is going to be the point of the arrow. Then 2, 2 is now 6, 2. That's the wing of the arrow. Then 6, 4 is the other side of the arrow. And then 4, 3 doesn't change because it's on the line of reflection. So hopefully yours looks prettier than that. Wanted us to draw the arrow to describe each of the functions and identify the line of reflection. So where is this line of reflection? At 4. And if it's a vertical line, what do we call that? Good, X equals 4. So the line of reflection is at X equals 4. Everybody okay with that? Okay, the next one that we're going to use is -2 minus X comma Y. Okay, so we're going back to these original points. What's -2 minus 0? Okay, what's -2 minus 2? -2 minus 2 and negative 2 minus 4. Okay, and then we keep our y's the same, just like that. So we get negative 2, 3, and we have negative 4, 2, negative 4, 4. That's going to be the top part of the arrow. So, no, is that? Yeah. Like how to connect the dots or whatever. Well, I'm like looking at it, it's original. That's what I'm like, that's how I just figured it out in my head. Like I said, okay, this 0, 3 is the tip of the arrow. So that means this point also has to be that very tip top. So it's going to like be the same location that it was originally. Like this 2, 2 is the bottom part of the wing. So this has to be the bottom part of the wing. Okay, so that's how I do it in my head. And then 4, 3 was the flat part, and now that's going to be at negative 6, 3. Just like that. Where is that line of reflection? Good, it's at negative 1. Okay, it's got to be directly in the middle of those. So if I'm looking at this, they both have to be equal distance from the line of reflection. So that one's going to be at negative 1. Okay, they're both 1 unit off. This one's point is 1 unit off. This one's point is 1 unit off. So that one is at x equals negative 1. Okay, now the next one is x comma negative y. Well, that one we know. There's no numbers involved. If the y is negative, what type of reflection are we having? It's over the x-axis, right? If the x stays the same and the y changes, it's going to reflect over the x-axis. But even if you didn't know that, because y'all were just steadily staring at me, you could still just do your points. Okay, so then we've got negative y, so negative 3, negative 2, negative 4, negative 3. So 0, negative 3. That's going to be the nose of the arrow. Then 2, negative 2, that's part of the wing. 2, negative 4 is the other part. And 4, negative 3 is the flat piece. And then we have our arrow. Where's that one's line of symmetry? You could say y equals 0. That's totally fine because it's a horizontal line at 0. Or you could say the x-axis. Either of those is cool with me. All right, 21, some of y'all probably heard me say don't do, some of you didn't, so we'll do 21. 21 says describe the reflection that would map the arrow onto itself. If you were going to map that arrow onto itself, what line would you use? It's going to have to be right in the middle of the arrow. So it like have you ever seen like, the only thing I can think of is like some kind of food on a stick where it just like rotates, you know? So it's like you've got to like find the very middle of that arrow so it just rotates around itself. Okay, so if we did this line here, which is y equals 3, the two wings just flop spots, right? And these two corners of the arrow just swap spots. The nose of the arrow won't move because it's on the line of reflection, so it just flips right there onto itself. Make sense? Okay, cool. All right, now the one below it says an irregular pentagon A, B, C, D, E has exactly one line of symmetry, which passes through point A. What is the image of point C under the reflection across the line of symmetry? Now remember, image is the second one. So it's saying when we have a reflection, where is it going to be? So it's like the after. They're looking for the after. So C is here now. Where is it going to go after the reflection? To D. So point C and point D are swapping spots. Okay. Then it says, does any point remain fixed under the reflection across the line of symmetry? Who? A and Y. It's on the line of symmetry. Any point that is on the line of symmetry is not going to move. Okay, it's on the line of symmetry. 24, which sides of the pentagon must be congruent? Which sides must be congruent? AE has to be congruent to who? AB. They must be congruent. And ED must be congruent to BC. Write those congruency statements if you didn't already do that. Those have to be congruent to one another or else it won't work. All right. Y'all go with that? We're almost done with lesson 9, and I will tell you, I'm not gonna quiz you on lesson 9 just because we just don't have the time. I don't want to do that next Monday, and we don't have class tomorrow. I would have done it tomorrow, but since we're off tomorrow, we're just gonna skip the quiz. Okay, that way on Monday we can start a new lesson and just keep rocking and rolling. But it is on your test. Okay, so don't just think because I'm not quizzing you, you won't see this again. It will be on Unit 2 test, okay? So all of this will definitely be tested. I'm just not going to give you a quiz because of time, okay? All right, page 120. Page 120 is all about rotations. Everything that we're going to be talking about today deals with a rotation, and the goals are pretty much the same as they have been all week, except for we're dealing with rotations instead of a translation or a reflection. So it says, perform rotations on and off the coordinate plane, identify and distinguish between reflectional and rotational symmetry. Okay, so we need to be able to decide, did they reflect or did they rotate? And how do we get that symmetry? Okay, cool. So it says, for the big finish of the Marching Cougars performance, Mr. Scott arranges the band in a triangle formation. Then the triangle appears to rotate clockwise around a point, like a pinwheel. The center of the rotation is the vertex located at 0, 0 on the coordinate plane. So you can see, if I was making like a pinwheel, this point right there is going to be the center, and I would spin it around that. Okay, everybody's seen like one of those spinners where you just spin it. It's around a central point, okay? Well, this central point is 0, 0. It says this spinning type of transformation is called a rotation. It is defined by the center of rotation, which is mapped onto itself, and the angle of the rotation. The center of rotation may be part of the figure being rotated, as is the case shown above, or it may be a point outside of the figure. Functions that describe rotations include, look at your rotation. Hold on, let me zoom. Okay, so it includes this function where you can see your y and your x switch, but also the x becomes negative. That's for clockwise 90 degrees. It says repeat the function twice to produce the next one. So your x and your y end up being in the right spot, but they're both opposite sides. That's for 180. And then this is for 270 clockwise or 90 degrees counterclockwise. Okay, because if you're thinking about a clock, and if this is my starting spot, and I go 90 degrees clockwise, I'd be going there, okay? if I wanted to go 180 degrees, that's going to put me here. But does it matter if I go this direction? Will I still get to 180 degrees? Yeah, 180 degrees. It doesn't matter if you turn this way or you turn this way, okay? Either way, you're going to end up facing exactly the opposite, which is a 180-degree turn. That's why they didn't say clockwise or counterclockwise, because it doesn't matter. But then this next one is 270, which is here, clockwise. So if we start here, we have to go all the way there to get to 270, or it's only 90 degrees counterclockwise. Okay, so that's why they specify clockwise versus counterclockwise. You're getting to this same location. You just have to decide if you want to go the long ways or the short ways. And it all depends on what they tell you to do too, okay? So we have a table just like before. You're just applying the function. So do that quickly. Number one, apply the function. Sorry. All right, did you get the same thing I got? You're just applying the rule. I almost forgot my negative over there on this one, but you got to change both the X and the Y. And so if it was already negative, it became positive. If it was positive, it became negative. So it swaps its sign. Any questions on applying a function to an ordered pair? Easy. All right. On the next page, we actually get to do some rotations. Now, they want you to make a prediction. It says, predict the direction of the arrow after these rotations. The center of the rotation is 0, 0. So this would be on a fan or a pinwheel or whatever. This is the center. So you decide what direction after a 90 degrees clockwise, 180 degrees, a 90 degrees counterclockwise. Make your predictions quickly. Where is it going to be pointing? Up, down, left, right. All right, I'm going to make us a little table. Okay, so the first point that I'm going to pick out is that point right there, which is at 10, 0. And then this wing over here is at 2, 6, because we're counting by twos. Then we have one at -2, 6. And then that base down there is at 0, 2. It's 0, 10. Let's see if I can erase that without messing everything up. Y'all see I made that mistake? 0 comes first, then 10. Okay, fixed it. All right, so the first thing that we want to do is a 90-degree clockwise. How do we show that with the function? If we're going 90 degrees clockwise, what happens? Yeah, we're going this way, but what's the function? Look at your notes and see what the function is. Okay, so we've got Y first and then the opposite of X. Okay, so my Y's need to come first. 10, 6, 6, 2. So put my Y's first. Then I need to make my X negative. There's no such thing as -0, so just 0. This one's going to be -2, and this one is +2, and this one is 0. Okay? Same thing with before. This 10, 0, 10 was the tip of the arrow, the nose of the arrow. So 10, 0 is the nose of the arrow. Then we have 6, -2. And we have 6, +2. Oh, we're counting. I'm counting wrong. Remember, we're counting by 2s. Okay. So that's like the top of my arrow. And then the base is at 2, 0. So did you say it was going to be pointing to the right? Yeah, good. Okay, what about clockwise? I mean, not clockwise. What about 180? It's going to be down. What do we have to get, or what is our function for it to be 180 degrees? Very good. Opposite of x, opposite of y. Okay, so we're changing both the x and the y. So 0 is still 0, -10. I'm going back to the original. That's a +2, so now it's a -2 and a -6. A +2 and a -6, a 0 and a -2. So you just change all the signs. Y'all are writing, right? So 0, -10, -2, -6, +2, 6, and 0, -2. Did you say down? Good. At least have it sketched on there. All right, 90 degrees counterclockwise. So what's the rule for that one? They switch. That's right. They switch, and y is negative this time. Okay, so I'm swapping my y's. My y's are going to come first. So I've got -10, -6, -6, -2. I put my y's first, and I made them negative. And then my x's, I just write them down. 2, 0, 2, -2, 0. And then we graph them out. -10, 0. -6, 2, -6, -2, and -2, 0. Then we have this beautiful arrow fan where it just rotates around. Do you see that everyone is 1 unit from 0, 0? Because that is the center of the rotation. Everybody stays 1 unit away from that. Think about a fan. If you've got a, like, what do they call those, blades? If you have a blade, one blade's not going to be closer to the center than the other one. Okay, they're all going to be separated equally out. That's why our fan spins perfectly and the blades don't get caught up. Okay, everyone is going to be exactly the same distance from the center of your fan. Well, the center of this is at 0, 0. Okay, all right. Number 4, describe the rotation that maps figure A onto figure B. So they've done it for us. We just have to describe what's happening. What's happening to figure A? Okay, so we're going 90 degrees clockwise. But who's going to be the center of rotation? Oh, you got the right point, but we're looking for an ordered pair. That's right, 1, 0. So that 1, 0 is our point that stays the same. So it rotates here, and then it would rotate down. If it rotated down, it would be like this, and then over here would be like this. So they all share that one little point right there at 1, 0. So that is the center. You see that? Okay, what happens to B down there? Good. 90 degrees counterclockwise. Who's the center of this one? For me, if it's hard for me to see, I try to find like the center of each of the shapes and kind of just like bring them together until I figure out where they cross. Like put the blade on a stick or something. Think about the fan. That would be my fan blade. So they would come together right there at that point. Do you see that? That's probably not the like mathematical way to do that, but it makes sense using your common sense. You find the middle of your image and kind of bring them together. So where's my center at? Good. Got it? Cool. We are rocking and rolling. All right, skip to page 124. All right. The way that they do in this book, all of the language for rotation is with that funny wording. I just want you to see it, okay? So if you look here, you've got the rotation, then you have the O, then you have the degrees. P represents your center. So it's a lot of stuff, okay? But you don't really have to get too caught up in any of that. We're not really going to be using that vocabulary or that way of writing it, but I do want you to see it so you'll know. So like it says, to describe rotations, we will be using the notation RO m to the degree parentheses P equals P prime, in which RO m to the degree is the function that the maps point P and point P prime with the center of rotation at O and through the angle of m degrees. Okay, so if we look here, you can see RO. So O would be the center, negative 90 degrees. Negative 90 degrees means that we're going counterclockwise. Okay, so if they make it negative, we're going back. This one says RC. So who would be the center? C. C would be our center of rotation, and we're going 90 degrees clockwise. Okay, RA. A is the center, and we're going 90 degrees clockwise. So any point can be the center. Doesn't have to just be like someone in the actual middle of the figure. You can rotate around any point, okay, on the figure or not on the figure. They identify that behind the R. R means we're rotating. The little subscript letter is your center, and then the degrees tell you which way we're going, okay? If it's negative, counterclockwise. Positive, clockwise. Got it? Cool. Now flip the page. 125. In our review your answers, don't review your answers. Figures such as squares have rotational symmetry, meaning that rotation of less than 360 degrees can map the shape onto itself. The smallest such angle is an angle of rotational symmetry. Identify whether each of these figures have rotational symmetry, reflectional symmetry, or both. Also, identify the figures of rotational symmetry and lines of reflectional symmetry. Okay, so if they have rotational symmetry, that means that we can spin it and get it back to itself, but it has to be less than 360 degrees. And we'll see some examples here. So if we look at the first one, an isosceles triangle, can I rotate that isosceles triangle and get it mapped back onto itself in less than 360 degrees? No. We'd have to go all the way around to get it back to itself. But look at the equilateral triangle. Can we spin that one and get it mapped onto itself? Yeah, you can, because look, it's equal. The sides are equal. So that means if I take this and spin it around itself, with this being my center, all I have to do is get this point to that point, and it's clicked back into itself. Okay, I could spin it again and go that way and get that back into itself and that back into itself. So do you see what I'm saying? Like, can you see that in your head visually? If I've got this triangle, I can spin it just enough to where, okay, it's back to where it needs to be, back to where it needs to be. Well, to figure that out, you have to say, okay, well, we're not going 360 degrees. We're going to go a part of that, not the whole thing, a part of that. How many times can we click it and get it back to itself within that 360 degrees? 3 times. So we take that 360, we divide by 3, and what does that give us? 120 is the angle of rotational symmetry. Okay, this figure has an angle of 120 degrees of rotational symmetry. Okay, but look at the first one, A. That one doesn't have one. Okay, it doesn't have any rotational symmetry, so we don't list anything. But does the first one have a line of symmetry? How many? Just one. Okay, does this B have a line of symmetry? How many? 3. Okay, let's look at the rhombus. How many lines of symmetry does the rhombus have? It has 2. Can we spin this and get this back to be mapped on top of itself? Yes. Okay. How many times could we do that? 2. So that's 180. Are you catching on to what's happening with our lines of symmetry in relation to our rotational symmetry? If it has a line of symmetry, more than one, that's what you're dividing the 360 by. This one has 2. That's what we're dividing the 360 by. So if you can identify how many lines of symmetry it has, then that's going to tell you what the 360 needs to be divided by. And in turn, that's going to give you your angle of rotational symmetry. Okay, I'm not giving y'all homework tonight because it's game night. It's homecoming. Y'all have a blast. Have a great weekend, and I will see y'all on Monday. So if you're in class, y'all don't need to turn anything in. Okay, if y'all are in class, you don't need to turn anything in. But those of you that are in the Zoom, if you're not in class, you need to turn your notes in. So take notes, take a picture of your notes, submit your notes.
I have a question about PSAT practice.
Uh-huh.
It says like find X